Hello, let's begin one more lecture session on sequence and series. In the last session, we have seen the concept of limit as well as convergence or divergence of a sequence. We will continue this topic and today we will see some important properties as well as theorems on the convergence or divergence of a sequence. However, first let us recapitulate for a moment what do we mean by a convergent sequence or divergent sequence. A sequence AN is said to be convergent if the limit of the sequence exists and is finite. That means limit AN n tends to infinity is finite. A sequence AN is said to be divergent if the limit of the sequence is not finite. This means that the limit is either plus infinity or minus infinity. There exists a third kind of sequence which is neither convergent nor divergent, and such a sequence is said to be oscillatory sequence. Let us now proceed to see some important properties. If An and Bn are both convergent sequences, then number 1, limit an plus or minus bn as n tends to infinity is equal to limit an n tends to infinity plus or minus limit bn n tends to infinity. Number 2, limit c multiplied with an n tends to infinity is equal to c times limit an n tends to infinity, where c is any constant. Third property, limit an multiplied with bn as n tends to infinity is equal to limit an n tends to infinity multiplied with limit bn n tends to infinity. Fourth one, limit an divided by bn as n tends to infinity is equal to limit an n tends to infinity divided by limit bn n tends to infinity, provided of course the denominator is not equal to 0. And the last one, limit an to the power p n tends to infinity is equal to limit an n tends to infinity whole to the power p, provided an is greater or equal to 0. Now let us look into these properties more closely for a moment. See that if An and Bn are both convergent sequences, we know that they will have finite limits, right? So let the limit An n tends to infinity be L1 and limit Bn n tends to infinity be L2. So then if we add these two sequences, limit an plus bn n tends to infinity will become L1 plus L2, a finite number. So what we can understand then from this property? If an and bn are both convergent sequences, then their sum will also be a convergent sequence because the limit of an plus bn will be a finite number. Similar conclusion we can have if we subtract two convergent sequences, and then also limit n tends to infinity an minus bn will be L1 minus L2, a finite number. Next, again if we have a convergent sequence an and multiply each term of the sequence by a constant c, then limit n tends to infinity can is equal to c times limit an, which is a finite number. So therefore we can again conclude that if we multiply each term of a convergent sequence by a constant, then the new sequence is also convergent. Again, if we have two convergent sequences an and bn with limits L1 and L2 say, then the product of the two sequences will be also convergent. This is what is told by this property, because now limit an into bn will be limit an multiplied limit bn, that is nothing but L1 into L2, a finite number. Very similar Interpretations can be made from the properties 4 and 5. Next, we will look into some important theorems. We will just see their statements without proof. The first one is every convergent sequence is bounded. Now, this is very obvious because a convergent sequence means that there is a finite limit and therefore the terms of the sequence cannot become unbounded. However, note that the converse is not necessarily true. Say for example, we have the sequence AN where the nth term is given by 1 plus minus 1 to the power n. So this essentially means that the sequence has the elements 0, 2, 0, 2 and so on. Now, notice that this is a bounded sequence because any element AN is bounded between 0 and 2. But we can easily see that it is not a convergent sequence because this sequence does not have any unique limit. So this is an example where the sequence is bounded but not convergent. The next theorem, a sequence which is both monotonic and bounded is convergent. So please see that a sequence is bounded. That is not a sufficient condition for the sequence to be convergent. However, if the sequence is both bounded and monotonic, it guarantees that the sequence is convergent. The third and the last theorem is the squeezing theorem. It's sometimes also called as the sandwich theorem. So what does it tell? Suppose that limit an n tends to infinity is equal to limit bn n tends to infinity is equal to L, and Cn is a third sequence such that Cn lies between an and bn for all n greater than capital N, where capital N is a positive integer. Then limit Cn as n tends to infinity is equal to L. So what does this essentially means? That if the sequence Cn is lying between two sequences An and Bn, so as if it is sandwiched between the sequences An and Bn, then limit Cn will be same as limit An and limit Bn, provided these two limits are same and equal to one limit L. Okay, so with these theorems and all this knowledge about convergence or divergence of a sequence, we will now proceed to see some examples that given a sequence, how we can check whether the sequence converges or diverges, or maybe sometimes it's oscillatory. So here the example is determine whether the sequence 2n plus 3 by 5n minus 7 converges or diverges. So here our an, the nth term of the sequence is 2n plus 3 divided by 5n minus 7. So in order to check whether the sequence converges or diverges, it's quite natural that we try to find out limit an as n tends to infinity. So that's what we try to do. So we try to find out limit an, that is 2n plus 3 divided by 5n minus 7 as n tends to infinity. Now what we do over here is we actually divide both the numerator and the denominator by the highest power, that is n over here, and this now gives us 2 plus 3 by n, and in the denominator we have 5 minus 7 by n, and now we take the limit of this expression as n tends to infinity, which we can easily observe is 2 by 5, because of course as n tends to infinity 3 by n goes to 0 and 7 by n also goes to 0. So we see that limit n tends to infinity is a finite number, and therefore we can conclude that the sequence is a convergent sequence and it converges to 2 by 5. Next example. Determine whether the sequence root over n plus 2 minus root over n plus 1 converges or diverges. So in this case, an, the nth term of the sequence, is root over n plus 2 minus root over n plus 1. So once again, we will try to find out limit an as n tends to infinity. And for that, we multiply this expression with this quantity, which is actually equal to 1, root over n plus 2 plus root over n plus 1. We take both in the numerator and the denominator. Now this gives us some advantage, of course. And now what happens to the numerator as we do the product? So the numerator becomes root over n plus 2 whole square minus root over n plus 1 whole square. That is n plus 2 minus n plus 1, and this is essentially 1. So finally, this expression reduces to limit 1 by root over n plus 2 plus root over n plus 1 as n tends to infinity. So with all this process, we have actually succeeded to take the n term in the denominator. And now as we take the limit as n tends to infinity, obviously the limit is 0. Once again, a finite number. So therefore, we can conclude that this sequence also converges. Next example. Write the formula for the nth term an of the following sequence and determine its limit if it exists. Does the sequence converge? So what is the sequence? The elements are as follows: 1 minus 2 by 2, 3 by 4, minus 4 by 8, 5 by 16, and so on. So let's first try to write down an. Now, of course, we can easily observe that the terms are alternatively positive and negative. So we will have a term here like minus 1 to the power n minus 1. And what is the numerical value? You see that when it's the third term, it's 3 by 4. So we can think of this as like 2 square. When it's the fourth term, it's 4 by 8, which is 2 to the power 3. Fifth term, 5 by 16, which is 2 to the power 4. So we can write this an as minus 1 to the power n minus 1 n by 2 to the power n minus 1. Now, having written an, notice that this minus 1 to the power n minus 1 multiplied with n, this term lies between minus n and plus n, right? So, using this fact, we can now write that minus 1 to the power n minus 1 multiplied with n divided by 2 to the power n minus 1. That is, we are writing here the expression for our an. This lies between these two numbers, minus n by 2 to the power n minus 1 and plus n by 2 to the power n minus 1. Now, we will try to find out the limit of these expressions using our L'Hospital's rule. So, see that limit plus or minus x by 2 to the power x minus 1 as x tends to infinity. As we try to find this limit, we can take out this plus or minus outside, of course. So this becomes plus or minus limit x by 2 to the power x minus 1, x tends to infinity. Now, of course, as we try to take the limit, this is an expression infinity by infinity. So applying L'Hospital's rule, what we get is plus or minus limit x tends to infinity 1 by 2 to the power x minus 1 log 2. That is, we are differentiating both the numerator and the denominator by x. And obviously now as we take the limit as x tends to infinity, the limit is 0. So now see that we can of course use our squeezing theorem, isn't it? Because if we go back for a moment, here our an is lying between these two terms, and we have seen that the limit of this as well as limit of this term is equal to 0. So therefore, by squeezing theorem or sandwich theorem, we can say that limit an is also equal to 0. And therefore, of course, because the limit is 0, a finite number, we can conclude that the given sequence is convergent. We will conclude our session with this example. And this is all about sequence also as per our course syllabi. In the next lecture session, we will start series. So thank you and goodbye till then.